G'day guys, welcome to another video on complex numbers. So as a review of where we're up to, we have gone through and defined a complex number in terms of a set, and then we've gone through the basic operations, addition, subtraction, multiplication and division. Hopefully we found addition and subtraction really easy, but multiplication and division were a bit cumbersome. Then we went into, well, why is it called Cartesian form when we represent a complex number in terms of that set? And we explain that because we can plot these things geometrically. And we do that on a Cartesian plane, but we give that Cartesian plane a special name, the Argand plane. Today what we're going to do is extend that idea. We're going to still represent these points on an Argand plane, but we're going to do it in a different way. We're not going to use the X and Y coordinates. We're going to do things a little bit differently. So let's jump into probably a visual way of explaining this, a geometrical way of explaining this, and then I'll show you the mathematical definition. Take any complex number, z equals x plus iy in Cartesian form, and plot it on an Argand plane represented by the point z. If we then connect up the origin to that point z, then the length of that dotted line we call the modulus, represented by r. We then take the angle relative to the positive x-axis and we call that the argument, here represented by theta. This is a very similar idea to how we developed trigonometric functions in the advanced course. That's mod arg form. Okay, so as on the screen it shows you there, mod arg form or modulus argument form is just another way of representing complex numbers. You've just seen it geometrically. It's a nice simple way of explaining things, and it's built up the same way that we built up trigonometric functions on the circle. So the methods that we use to solve trigonometric problems are going to be carried over here to how we solve problems with complex numbers as well. So the mathematical definition, here it is here. It's wordy, but it's basically what we just showed on the screen. If we take a complex number z equals x plus iy in Cartesian form, then the distance between it and the origin in a straight line, we call that the modulus, and we'll use the symbol r for that. And essentially we'll just be able to use Pythagoras or the distance formula to calculate the length of that modulus. And then we represent the angle between the positive x-axis and that complex number. That's the argument. It's going to be an angle, and we'll be able to use trigonometry to calculate that angle. And once we do that, just like we built up our definitions of a trigonometric function, if you remember your circle definition, when we had the point on the circle, its x-coordinate was cos theta and its y-coordinate was sine theta. So hence here we can just change our complex number z equals x plus iy into the equivalent form z equals r times cos theta plus I sine theta. So let's go through an example. Here I've got a very simple complex number, z equals 1 plus I, and we're going to turn that into mod arg form because we can plot that on an Argand plane really easy. Its x coordinates 1, y coordinates 1, so it's just represented by the point 1, 1. So we can plot that on an Argand plane nice and easily. Now to find the modulus is just the distance or the length of that line there from the origin to the point z, and I can just use the distance formula or Pythagoras here because I can form a right angled triangle, and using Pythagoras I'm going to get that r is equal to the square root of 1 squared plus 1 squared, which is just root 2. Okay, so the length of that line is root 2. That's what we call the modulus. Okay, then we need to find that angle between the positive x-axis and this new modulus, and we can just use trigonometry for this. If I use that angle, I can form a right angled triangle, and the opposite and adjacent sides are both going to be 1. So when I take tan theta, or the inverse of that to find the angle, I'm going to get 45 degrees. So I can represent this complex number, z equals 1 plus I, in another form. I can say that it is equal to root 2 cos 45 plus I sine 45. I know at the moment it probably seems cumbersome. Why would I be doing this? But you're going to see why we're going to be using this. It's actually going to make multiplication and division much, much easier. Now I can do a second example, a little bit more complicated. Here's z equals -1 plus root 3i. Again, we can plot that on the Argand plane. Be mindful here, this is in the second quadrant, so we're going to have to be careful when we're calculating that angle theta. But other than that, it's going to be pretty straightforward. I can form my modulus, that line there. All we care about is the length of that line, okay? Here I can just use Pythagoras to solve that problem. R is equal to the square root of -1 squared plus √3 squared. And when I simplify that, I get 2. So the length of that line is 2. That's the modulus. Then I can calculate the angle. And here I'm going to use my, kind of like my reference angle, alpha. So, or I could call it my intermediary or my auxiliary angle that I'm going to calculate here, because I can use a right angle triangle here. And then I can work out what theta is on the other side, just like when you were working with your circle definition for trigonometry here. So tan alpha here is √3 and 1, opposite over adjacent. I don't care about the fact that I'm at -1. All I care about is the length of the base of that triangle's 1. I'll worry about whether the angle's positive or negative once I've solved the problem. Just like, again, like you do with circle geometry, circle trigonometry. So my angle there would be 60 degrees. That's just an exact value triangle, but that's alpha. So to find theta, the other side of that, I've got to do my 180 minus theta, or 180 minus alpha, and I get 120 degrees. So now I know what R is, I know what theta is. I can write Z as 2 cos 120 plus I sine 120. Third example, getting more complicated again. Z is equal to -√3 minus I. So when I plot this one this time, it's in the third quadrant. Again, I'm going to have to be careful of angles here when I'm working out theta. So I can draw that on my argand plane. It's always a good idea to draw it on an argand plane, because then you know what quadrant it's in, and then you can work with your angles appropriately. So R is always easy. It's just Pythagoras. Just chuck it in. And again, here we get that R is equal to 2. My angle this time is tan alpha is 1 over √3. Again, remember, I don't care about the negatives here. I just want to form my right angle triangle and work out what the angle inside that triangle is. I'm calling that alpha, my intermediary or my auxiliary or my reference angle, whatever you want to call it. And I can use my exact value triangle again here and get that angle alpha is 30 degrees. Now I can use my kind of all stations to central idea. I know it's in the third quadrant, so it's going to be 180 plus alpha, and I'm going to get 210 degrees. Okay, I'm actually going to leave that one to you to write down in mod arg form, and then I guess you can let me know what you got, and hopefully you got the right angle, the right answer. All right, so another example. This time we're going to work backwards. We're going to start in mod arg form, and we're going to get back to Cartesian form. So this is important. Often in questions, and I've hinted, multiplication and division questions, mod arg form is going to be useful. So we'll probably get given the initial question about a multiplication with the two complex numbers in Cartesian form. We'll have to convert them to mod arg form to do the calculation, and then at the end, convert the answer back to Cartesian form. So here's an example of how we can do that. And we can either use our knowledge of exact value triangles, or we could just plug things into a calculator. So here I've got two complex numbers, Z1 and Z2. Let's look at Z1 first. Z1's 2 cos 60 plus I sine 60. Again, I can just use my knowledge of exact value triangles, or I could just plug cos 60 and sine 60 into the calculator and see what it tells me. Just make sure you're in the correct mode when you do that. Okay, so if I do that, I get cos 60 is a half, and sine 60 is √3 on 2. So therefore, I can simplify the brackets. Instead of writing cos 60 plus I sine 60, I can write a half plus √3 on 2i, and then I can just multiply through by that 2, and I get 1 plus √3i. Okay, so now I've got it back to Cartesian form. I can do the same thing for Z2. I can just plug in cos -300 into my calculator. Make sure you put brackets around the -300. See what it tells me. Do the same thing for sine. And again, I'm going to find out that cos of -300 is a half. Sine of -300 is √3 on 2. And therefore, I get the same complex number again. So this is important. That angle that we're given there, 60 or -30, I've said that's called the argument. We can represent that. We can write arg z, arg, and then in brackets z. We could write arg z for z1 would be 60, and arg z for z2 would be negative 300, and that would have a lowercase a. Argument would have a lowercase a. And here what we've discovered is that the same complex number can have different arguments. But if you look carefully, it's all that's happened is I've taken 60 and I've gone backwards 360 degrees. I've gone around the circle and I get to negative 300. I can just keep going around in lots of 360, sorry, and I'll keep getting back to the same point. So it's really the same angle. It's just it looks different because it's off by 360 degrees. So to make sure that we always get the same answer, that we're always going to get just one answer pop out instead of lots of different answers in multiples of 360, then we can make a restriction. And we're going to call this the principal argument, and we're going to use a capital A for this. So what we want to do is define our principal argument to always be between negative 180 and 180. So in practice, what that means is if you're doing a calculation and your argument here comes out, say, as negative 300, then you can just subtract or add 360 to it until you get between negative 180 and 180. So all I have to do here to negative 300, if I got an argument of negative 300, that's not between negative 180 and 180 like I want. So I could just add 360 to it. And if I do that, I'm going to get that angle of 60. That's between negative 180 and 180. So that's what I would call my principal argument. Then we're always going to get the same answer. You'd get the same answer as I would for the argument because we're making sure it's always in that range that we want. Okay, so that's all principal argument means. Okay, so now let's start using this idea of mod arg form. It's going to be quite powerful, and we're going to see that multiplication and division are really easy. Once we're in mod arg form, multiplication and division are going to be really easy. This is going to utilize one of our extension 1 trigonometry results to do with additions and subtractions of angles, and I'll point that out when we get there. So we're going to demonstrate how do we multiply two complex numbers together. So I've already put them in mod arg form here. I've called them Z1 and Z2, and you'll notice they've got different modulus, R1 and R2, and they've got different arguments, theta and alpha. Okay, we're going to multiply them together. So I've got those two brackets, and we're just going to do our expansion just like we've learned how to do with multiplication earlier, but then we're going to see there's a really nice shortcut to this. Okay, so I'm just going to expand it out. And first thing I'm going to do is multiply the two moduli together, R1 and R2. I'm going to keep the brackets, the rest of the brackets unaffected. Okay, so straight away I can see that my modulus of the two complex numbers, they're just going to multiply together. Okay, then I can expand my brackets just like I've done before, and I've collected real parts and imaginary parts. So the reason we end up with a negative sine theta sine alpha here, if you look carefully, it's because I'm going to do I sine theta times I sine alpha, and those i's, when they multiply, are going to give me an I squared, which is a negative. Okay, so that's where that negative sine theta sine alpha came from as a reminder. So I've got a real part and I've got an imaginary part, and this is where I've got to utilize my extension 1 results. So if I recall back to my trigonometry in extension 1, I know that if I do cos theta plus alpha, that's this thing, cos theta cos alpha minus sine theta sine alpha. It's on your reference sheet if you look carefully, so you can see it there. And similarly, if I do sine theta plus alpha, it expands out to sine theta cos alpha plus cos theta sine alpha. So that's just extension 1 results where that's come from. And why this is useful is, well, once we're in mod arg form, then multiplication, all I need to do is multiply the moduli and add the arguments, with the proviso that if that argument then ends up outside of negative 180 and 180, add or subtract 360 as appropriate to get your principal argument back. Okay, but it's really easy to do multiplication. I guess the lengthiest part is putting it into mod arg form, and then the multiplication is easy. Just multiply the moduli, add the arguments. Division is no more complicated really. So again, I've got them in mod arg form already here, and I'm going to divide them, which I've written as a fraction here to make things nice and easy. So I'm going to split off that R1 and R2 separately, and then all I've done here, just like we've done with our multiplication earlier, I'm going to multiply top and bottom by the conjugate of the complex number, which just means replace that positive with a negative. Okay, I'm going to expand the brackets top and bottom, and the great thing about multiplying by a conjugate is that the denominator just becomes a real number, cos squared alpha plus sine squared alpha, which is just 1. So that's quite nice. We got rid of the fraction. So far we can see that the moduli are divided, and we've got a real part and an imaginary part here again, just like before. And again, extension 1 results, I can see that that's cos theta minus alpha as the real part and sine theta minus alpha as the imaginary part. Again, it's on your reference sheet, just look carefully for that. And then it's an extension 1 result. So again, division is nice and easy once we're in mod arg form. We just divide the moduli, subtract the arguments, again with that proviso, if the argument's not ending up between negative 180 and 180, just add or subtract 360 until you are. And that wraps up today's video on mod arg form.